Good afternoon, ladies and gentlemen. I'm Zhuolin Wang from the University of Warwick. First of all, please let me express my sincere apology for the absence of making this presentation in person. The topic I'm bringing here today is adaptive model predictive control for thermal management for electric vehicles. This study is making contributions to the improvement of battery performance in the future from the temperature control aspect, which is related to the enhancement of overall vehicle efficiency. Here is the content of this presentation, which has 4 parts. This study establishes the physical model of temperature control of battery and control system on this basis. The comparison between PI controller and adaptive MPC in simulation shows the feasibility and effectiveness of the proposed controller. First, please let me introduce the energy macroscopic representation. EMR was developed as an approach to analyze and control electromechanic system, which has been extended to cover various energy conversion systems, including hybrid electric vehicle and others. EMR is based on the interaction principle of seismics and causality principle of energy. It represents the energy flows and interactions between different components of a system, so allowing a better understanding of its behavior and the development of control strategies. So it provides a systematic and visual representation of energy flows, making it easier to design and analyze control schemes for complex systems. So it has been used in both academia and industry. Therefore, it is chosen here for the BTM system. So according to the existing literatures, the challenges in BTM lies on these 4 aspects. First, battery exhibit a nonlinear behavior in response to temperature variations. Therefore, the control strategies are sophisticated for accurate prediction and management of these changes. Second, the thermodynamics of the battery's function are at a lower rate compared to electric drive units, so longer periods optimization is needed, which makes the system complex and uncertain. Third, the performance of battery thermal management system is closely linked with the overall functioning of the vehicle. The optimal balance between the efficiency and effectiveness of both of these elements is of importance. Fourth, effective cooling is crucial for preserving the health of the battery. However, it is important to achieve this without excessively draining the battery's energy reserves. So the challenges BTM is facing lead to the needs that the controller has to achieve. The design of the controller needs to be able to cope with the complexity, uncertainty, and integration to the overall functioning of the vehicle. Meanwhile, it needs to obtain the efficiency and effectiveness of the use of energy. So many methods have been proposed for achieving the control goals. PI controller together with fuzzy logic methodologies are simple and effective solutions for maintaining temperature within desired limits. Also, model predictive control has shown its potential by utilizing predictive models to adjust thermal conditions in anticipation of future battery behaviors. And for this nonlinear system, the incorporation of advanced machine learning techniques has proven effective in understanding thermodynamics and developing adaptive control strategies. So in this study, the aim is to design an adaptive model predictive controller for battery thermal management to achieve the needs mentioned just now. So the adaptive MPC is considered as an advanced control strategy with precision. So they established a generic thermal model for the battery with a single equivalent control variable, and the optimization task involves managing a multi-input and single output scenario. The inherent nonlinearity of the thermal model is toggled by using the Taylor series linearization technique around the nominal operational point. Also, the plant model is updated consistently with each interval to ensure the accuracy and relevance in the control process. The control system shows a thorough understanding of the dynamic relationship between thermal management and vehicle performance. So the physical model of BTM is presented here because the change of internal resistance of the battery is related to the charging and discharging state of the battery. So the open circuit voltage of the battery is coupled with the operating state of the vehicle. As presented here, the battery temperature is relevant to the functioning of the traction system and the environment. So the control variable here of the system is the BTM power given by the controller, which is considered as the system terminals together with the system traction power and environment temperature. So based on the physical model, the PI controller is designed with an inversion-based control for the generation of BTM power. The control parameters and transfer function are presented here. So the temperature of the system is controlled by the PI controller with this feedback control. So the principle of the adaptive MPC is shown here. A predictive model of the system is utilized to forecast future behaviors and optimize control inputs over a limited time horizon to achieve desired performance. The model parameter estimator updates the parameter based on the plant output within each interval to obtain the adaptiveness of the controller. Therefore, the state space model is linked with the adaptive MPC module here. So according to the physical model of the BTM, necessary inputs of AMPC module are set. To utilize the adaptive MPC, the state space equation of this system is established. The system has 2 state variables and 3 input variables. The performance of the controller is controlled by these 3 inputs and observed through the change of the battery temperature and the state of charge. Because the BTM system is nonlinear, the continuous updating of the predictive model is accomplished by the model parameter estimator after the linearization. The system is linearized using the Taylor series. The nominal operating point is supposed here. And the Taylor series expansion of the state variables are shown here. The coefficients in front of the input variables are their corresponding coefficients in those metrics. As presented here, the coefficient matrix of the state space is obtained. So at this point, the necessary requests for setting up the AMPC module have been prepared. So based on the designed control system, the simulations are done and the results are presented. First, the urban driving cycle is used to test developed adaptive MPC controller, assuming an initial battery temperature matching the ambient temperature of 22 degrees and a target temperature of 25 degrees. The battery temperature reaches the set point after approximately 100 seconds, and subsequently it remains stable at this temperature. So the designed adaptive MPC controller demonstrates effective temperature control over the battery and achieving the desired outcomes. Then the comparison between PI controller and adaptive MPC are done on the performance at the highway cycle of using the two controller under ambitious scenarios, with the limitation of BTM power is minus 1.5 thousand watts to 1.5 thousand watts. One is the simulation of a summer environment, keeping the set point at 25 degrees and assuming the environment temperature and the battery initial temperature are both 38 degrees. So the simulation results of each controller are presented separately here. In AMPC, the battery's temperature is reduced to the set point after approximately 500 seconds. After the stabilization time, the temperature remains stable at the set point in the subsequent running time. And as for the PI controller, the battery temperature can be reduced to the set point as well. However, the stabilization time is slightly longer than using adaptive MPC, which is approximately 600 seconds. Meanwhile, there is a slight difference in energy consumption. The other scenario is the simulation of a winter environment. The environment temperature is assumed as minus 20 degrees, and the initial battery temperature is 20 degrees, assuming that the temperature is preconditioned to have better discharge capability. The set point is still 25 degrees. In AMPC, the battery temperature can reach the set point after approximately 180 seconds. After the stabilization time, the temperature is maintaining around 25 degrees with tiny vibrations. But the use of PI controller managed in increasing the temperature after approximately 180 seconds as well. However, there is a steady state error exists in the whole process of the simulation, with the same PI parameter as applied in some environment. So the possible reasons of the error might be the proportional parameter and integral parameter here are not very suitable, or the limitation of the BTM power, just said it before. So the comparison of the adaptive MPC and PI controller is in this table. In summer environment, the adaptive MPC reaches the control goals with only 0.8% more power consumption than PI controller. The slight difference of energy consumption is possibly the reason of shorter stabilization time of adaptive MPC comparing to PI controller. In winter environment, even though the stabilization time of using these two controllers are similar, the model with PI controller is worse at reaching set point temperature. So relatively, the system with adaptive MPC maintains the control results more stably. And the comparisons between adaptive MPC and PI controller in general is presented. Comparably, PI controller is simpler, but the adaptive MPC has better performance in constraint handling, model flexibility, and in energy efficiency. However, it is more complex in computation. In addition, they both have a relatively high model dependency and are not performing very well in nonlinear systems. So here are the conclusion and future work of this study. The simulation results and comparison showed the controller's capability to reach and maintain the desired battery temperature set point and its significance in stabilization time and control performance. So this work contributes to advance the field of battery thermal management control strategies, paving the way for more effective and adaptable approaches in real-world applications. As for the future works, redefining the mathematical deduction on model linearization is one of the aspects that need to be paid attention to. The current battery resistance is obtained by simple lookup tables, which neglects the impact of temperature and state of charge on battery resistance, so the internal resistance can be more accurate. For instance, it might be a function of the battery temperature and the state of charge, so which can be approached by nonlinear regression in future deductions. And here is my list of references. So this is the end of my presentation. Thank you for listening. You are more than welcomed to discuss and share opinions. Thank you.